You don't know. This will automatically, that's what automatically it will do. When you start your system, this will automatically will start operating during when system is started. Yeah, it will be part of your design actually. So initially when your VDD is settled, then you operate this actually during startup. So that's the one way. Other way, so then in that case, every time you start your system, you have to do that. Another way is what you do actually during testing, you do this and burn the code on the ROM, and then it will fix your register value in that case. So both ways are used actually. If you don't have a ROM option, then you have, every time you have to do, because your those codes will be stored in the flip flop. Okay, and every time you turn off your system, the code will get reset. So you have to do every time. But if it is stored in the ROM, then you don't have to repeat it again. So and that's why if you stored in the ROM, you mostly do it during testing. So whoever buys your chip, that will get a burnt code in that case. So in that case, it will not change. Okay, so both techniques are used, ROM as well as RAM. And sometimes during testing, it's not burnt in the ROM, still you want to store. So during testing, you find what is the code, okay, and that code is stored in your startup file, like a BIOS in computer you have. So when your system starts, it will load those codes, and then properly your phone or whatever computer will start up after that. So there are various techniques which are used in the software, hardware, everything, whatever the requirement is, they apply that. So during boot up you use, so that is called your boot file you use, and the boot file will have an initialization code, and that will just write those codes to these flip flops, and it will start with that. In that case, you don't have to do every time that iteration. Okay, so those were static offset cancellation. Now let's look at dynamic. Okay, so we'll take the same example, your balance. So we know my balance was faulty. Now go back to the original. You don't shift the center, because shifting the center means you have corrected. So now since we are using a dynamic offset cancellation, so we will not do the correction. We will just use that faulty balance. And so we know that, let's say error is 100 gram was the error. Okay. So if you want to buy 1 kg fruit, you will get 900 gram only. Okay. So now you go back to the again that shopkeeper and play a game with him. Okay. So just tell him, I want to swap the my fruits and weights. So he will not do that. He will say now he will have to give you 1.1 kg. Okay. So ask him, you split into half kgs. One time half kg weigh from this side, and other half kg weigh from this. So this half kg will give me 400 gram, other half kg will give me 600 gram. So you will get perfect 1 kg. Okay, and that's what you do in dynamic offset cancellation. What you do, you know your offset is in the one direction, either positive or negative. So use a clock and keep swapping every clock cycle the positive input and negative input. That's it. So you apply a plus offset on the other side, then you apply a same offset on the other side in another cycle, and they will get automatically cancelled out on an average. Okay. So 1 kg is broken into 2 half kgs and weights and fruits are swapped for each lot. Okay, so this is your 0.5 kg weight, and then you have your fruits. So what you get here, it will give me 400 gram due to error, correct. So second part, you just do this. .5 kg, so it will give me due to so total equal to 0.4 equal to 1 kg. Okay, so your error is so what you do in the amplifier, so each amplifier has 2 inputs and 2 outputs, positive and negative. Okay, and since I am operating in the feedback, I have to ensure that when I change the inputs, it should still be operating in the negative feedback, which means when you are changing the input, you have to change the output also, so that your negative feedback is maintained, otherwise this will not work. So if this is Vref and this is your feedback voltage, let's say, then what you have, you have 2 switches VFB, and similarly you have 2 switches here, one will, other will Vref. Okay, and then you have 2 switches here. So if this is my plus and this is my minus output, and this is your V out. So let's see, at phi this is Vref, this is VFB, at phi bar this is VFB, this is Vref. So at phi this is V out, and sorry, and at phi bar. Okay, you change inputs and outputs both, so your negative feedback will be maintained and your offset will be cancelled out. And usually these are non-overlapped clocks, so okay. So what would happen at the output if you keep doing this? You know, offset, so output will be looking like this. Instead of a constant DC, so let's say you had an offset. So depending on whether offset is positive or negative, your output will be a DC, whatever your desired output is, minus or plus V off. Okay, but now you are basically shifting the offset in both the sides, so it will keep doing this. okay, and average will be whatever, let's say V out is 1.2 volt and this will be 1.2 volt plus V offset, and this will be 1.2 volt minus V offset, correct, but average will be, so you will get a ripple, so your ripple will be plus minus twice of offset, peak to peak ripple. So if you can afford to have that ripple, then it's fine. If you cannot, then this method will not work in that case. So the only way it will work, you have to filter out this ripple by putting a low pass filter at the output, and then you can get it work. So use a low bandwidth low pass filter and filter these. Okay, and if your system is very, so let's say this output is going to some next stage which is by default has a very low bandwidth, then that will automatically filter it out. But if not, then you have to apply some filtering. So for most of the time your it's good enough, your static offset cancellation is good enough for regulator application. This is mostly used for very high accuracy application in the instrumentation and all those like ADCs. Okay. So other ways you combine the both. So let's say your offset is 10 millivolt. So I would be seeing like plus minus 10 millivolt ripple, which is quite huge. So what you do, you 10 millivolt, you can brought it down to 1 millivolt by using offset, static offset cancellation, and now you apply this, so your ripple will be only plus minus 1 millivolt. So that's another way to reduce this ripple.
Using static, we are reducing the.
With the static, so if I want to reduce, let's say with the static I want to reduce by 100 times, then I know it will require a very high resolution DAC or all those resistors, which will make it very complicated. So what you do, you just use a 3 or 4 bit resolution there. So you know that your maximum offset can be 10 millivolt. With 3 to 4 bit you can bring it down to, or with the 4 bit bring it down to less than 1 millivolt. Okay. So now after that, if you apply this dynamic offset cancellation on top of that, your ripple will be only plus minus 1 millivolt or less. But if you don't use static offset cancellation, then all the offset is now getting corrected by this dynamic. So your ripple will be larger in that case. Okay, so most of the time we combine the two techniques. You first do the static offset cancellation, bring it down to whatever easily you can do with the design, 1 millivolt or so, and then on top of that you apply this dynamic offset cancellation. Okay. So this technique is also called chopping actually, because you are chopping the input. Now it's not a continuous, but you are chopping the input basically. You are sampling the input and just swapping the input. What could be the other way? Any other way of doing this dynamic offset cancellation? So let's say I have this plus minus, I apply Vref here and I apply VFB here in the feedback. Okay. So if it has an offset of, let's say, plus VOS, and if I connect it in the feedback, what would happen? Hmm?
VREF plus VOS.
Where will this output go? Hmm? This will go to VREF plus VOS. Okay. So now if we add a cap here, this will store VREF plus VOS. So you had a plus VOS, which means at a positive terminal, instead of VREF it was looking at VREF plus VOS, correct. So which means if I apply the, instead of VREF plus VOS, if I apply the VREF minus VOS, then but how will you do VREF minus VOS with this? Or what could be the other way? So you apply VREF minus VOS, or you apply a VREF V in plus or whatever VFB you are applying, you add that offset in the VFB. Both are same, huh? Either you subtract there or add on the other side. Okay. So what we do actually, we connect this terminal to VREF. Now where will this go? VREF plus VOS? It doesn't matter where the bottom plate is connected. Huh? So now how much voltage is stored? Okay. Now if I take this capacitor and apply a V in here, where or VFB, where will this go? V plus, because capacitor voltage does not change. Whatever is stored, it will remain stored. So what you are changing, only changing the common mode level on which this is floating. Correct. That's how switch cap works actually. So any cap, if it is connected to any V voltage, and if this is V plus delta V, so no matter what you apply here, if you give a 2V here, then this side will go to 2V plus delta V, because this delta V will be maintained by the cap. Okay. The common mode voltage will keep moving, but that capacitor, whatever capacitor is storing, it will remain stored across the cap because it cannot change for a floating cap until unless you connect the other side to ground. If you hard connect to ground, then whatever you charge it, that charge will be stored, and that's what you are doing here. When you are connecting in the unity feedback, this other side is considered as good as ground, VREF. So you charge it to fully at VREF plus VOS, and then you change the other plate. So this will change. So in the next phase, you apply a VFB plus VOS, and that offset will get cancelled out. Okay, so same thing you require here. I am not showing the phi and phi bar, but you require switches and this capacitor. So one switch will connect to here for unity feedback. So let's say phi, and then this capacitor output also needs to be changed. So you will have again 2. So phi will connect to VREF and phi bar will connect to VFB. So this is called auto zero actually. So you connect it in the unity feedback, store the offset, and then in the next cycle you cancel that by adding or subtracting that offset from your feedback voltage. Okay, so if you are doing on the VREF side, you have to subtract instead of adding. So in the switch capacitor circuit, most of the time you use this, because by default switch capacitor circuit has a clocks, it's a switching circuit. So you can easily apply these concepts there. But in the continuous time, this is some extra overhead you have to add.